All right, welcome to AP Chemistry. We're going to go ahead and start this year on units 1.1 through 1.3. And so let's look at this right from the get. We have our instructions. You should be reading unit 1 from the AP Prep book, and then all sections embedded in here. Obviously, there's going to be a quiz on this. I encourage you to use the Desmo Scientific Calculator, or if you have a handheld calculator that you like to use, you're more than welcome to do that. And then also reference your resource sheet. This is the periodic table that you get to use on the AP exam. So I encourage you to use this periodic table for all of your assignments. That way you're familiar with the resources that you have available on the tests. All right, so on this unit 1.1, it's going over moles and molar mass. You should be able to calculate quantities and its relative number of particles using dimensional analysis and the mole concept. We remember that the mole is a unit for counting, and sometimes particles cannot be counted directly while performing laboratory work. So we have to make a connection between mass and the actual number of particles undergoing chemical changes. The moles and molar mass, we should understand that the mole is a value of 6.02 times 10 to the 23rd. And then when we look at our periodic table, we can find the molar mass of elements from the periodic table. For instance, we can see that carbon has a molar mass of 12.01 grams per every 1 mole, whereas nitrogen has 14.01 grams for every 1 mole, or 12.01 grams of carbon for every 6.02 times 10 to the 23rd atoms of carbon. And so we should be familiar with the mole concept and how moles relate to mass in the periodic table coming from your previous chemistry course. And then we use we use mass because counting particles is way too hard. And so we have to relate to a value that is easier to obtain, and mass is a much easier value to obtain. And so we should know already between Avogadro's number and the mole. And so you can read that on your own. And then we have, looking at the molar mass of compounds, we have water, for instance. We notice that we have 2 hydrogen in 1 mole of water, and each mole of water is 1.01 grams. We get that from the periodic table here. It says 1.008. Probably should have used that value. But we rounded up here 1.01. And so we get 2.02. And then there's 1 mole of oxygen for every 1 mole of water. And so we take those values, we add them up, and we get the molar mass of the compound to be 18.02 grams per mole. When we use dimensional analysis, we're converting from one unit to another. And here we're converting from mass to moles. This is a very common conversion. And here I just want to show the setup for dimensional analysis. We show a given unit. Again, here we're converting between 25 grams to moles. So 25 grams of water to the number of moles of water. We notice we start with a given unit, which is 25 grams. We use the molar mass as a conversion factor to convert from grams to moles. And so we get this molar mass, as we saw here. We see that 18.02 grams is equal to 1 mole, and now we can convert to moles. So 25 divided by 18.02, we land at 1.39 moles of water. And so this is using dimensional analysis. It is required and is part of our standard, right? Again, using dimensional analysis and the mole concept. So here in that example, in this example, we see dimensional analysis and the mole concept. Here is the mole concept being used in that dimensional analysis setup as a conversion factor, as a matter of fact. So in example 1, we're going to use all those skills in example 1 to determine the formula unit of a hydrate. And we talked a little bit about this in class, that a hydrate is a compound, in this case an ionic compound, copper 2 sulfate, and then we call it copper 2 sulfate pentahydrate, penta meaning 5. So this has 5 water molecules associated with each formula unit. So copper sulfate picks up 5 moles of water, maybe from the air, or it just naturally absorbs water. And this is where we say the amount of water that it absorbs. And so when we get a container that says that we have copper 2 sulfate pentahydrate, we can't assume that all of this substance that we obtain is copper 2 sulfate, because it also has water with it. And so we would, if we were to assume that we had, for instance, 100 grams of copper 2 sulfate, and we have 100 grams of copper 2 sulfate pentahydrate, we would have far less copper 2 sulfate than expected, because there's a lot of water on that hydrate. So in this experiment, we are taking a hydrate and we are weighing it, and we weigh that hydrate and we see that it's 2.497 grams. And then we heat the hydrate to remove all of the water from the hydrate. Now, this may take several heatings. I simplified this table here, but you may have up to 3 or 4 heatings. And every time you heat, you're looking to see if there's a mass change. And so if you see the mass keeps going down with each subsequent heating, well, then you know that you've driven off a little more water and a little more water. Once you get to a point where the mass remains constant, then you know all of the water has likely been driven off of the salt, and you can be confident that you have what is now called an anhydrous salt. And the anhydrous salt is meaning that it is not a hydrate, meaning there is no water associated with it. Why? Because it was heated and all the water was removed. So let's go ahead and get started on this. We are going to figure out what is the mass of the water, how many moles of water, and then the formula of the hydrate from this scenario. So this is actually fairly easy, because this first part, we're going to go into show your work. And what we see here is that we need to calculate the mass of the water. Well, we see we have the mass of the hydrate, and then we have the mass after heating. Well, this is the mass of the hydrate. It has water. This is the mass of the anhydrous salt without water. So the difference in these two values is the mass of water. And so that's what we're going to show. And we have to always label our work. And if this is part A, we're going to label it part A. And we're going to say the mass of water. And we can say this is equal to mass of hydrate minus mass of, let's say, anhydrous compound. We'll just say mass of anhydrous. Okay, so there we go. So that is going to give us the mass of water in the hydrate. So how do we know we have an anhydrous? We just drove off all the water by heating. So now we're going to just plug in those values. This is equal, what is the mass of the hydrate? It is 2.497 grams minus the mass of the anhydrous, which is 1.597 grams. And we see that we get, 0 equals 0.900 grams of, in this case, water. So we're going to say water, because that's what this is. This is the water. So we know that hydrate has 0.9, or at least that sample of the hydrate has 0.900 grams of water associated with it. And so that's our answer there. If we want to, we can, and we really need to show our answer. We go ahead and copy the answer, and we just paste that right into the answer box, and done. And we should get credit saying that we got some points for that. All right, I'm not sure it shows it on my screen that I get exam, but I'm using the teacher version and your student version. So we can go to part B, and then part B, we can see that there's not a need for a line there, but just separating my work. So B, we're going to calculate the moles of the anhydrous salt. Well, how am I going to do that? Well, first, I'm going to look at this. The mass of the anhydrous is 1.597 grams. I want to know how many moles that is. So I've already put in a B here and add math. If I go ahead and hit add math and then click on B, there it is again. So it's not hard to come back to. And I'm going to start with 1.597. 1.597 grams of, and this is the anhydrous salt, and it happens to be copper 2 sulfate. So that's CuSO. And then if I hit shift and the dash, that's the button right next to the 0. I can subscript. If I want to get out of the subscript, I hit the over arrow, and that comes up. Now I'm going to show dimensional analysis by multiplying by a conversion factor that will take me from mass to moles. Now I'm not going to show my calculation for the molar mass of copper 2 sulfate. I expect you to know it. I expect you to know how to do it for a quiz. I expect you to know that you need this value on a quiz. And so the value that we obtained is 159.61 grams of copper sulfate. And quite frankly, you don't want to type copper sulfate over and over again. You can highlight, hit Control C, and then when I need to put it in here real quick, I will be able to do that. And this is going to be equal to 1 mole of copper 2 sulfate. And so there it is. And see how quickly I got that in there this time. And so now all I have to do is plug this into my calculator, 1.597 divided by 159.61. And what I end up getting is 0.01001. And this will be moles of, watch that, copper 2 sulfate. And I just copy and pasted that part in there. And then now what I'm going to do is copy my answer, Control C, save, hit save for sure. You don't hit save, you might be redoing that work. That's not good. Nobody wants to redo work. And then just place your answer into the answer box. And you should be getting credit for that. All right, next, we're going to go to part C. Again, you don't have to separate with lines, but I do like you to label your parts so that they're easy to see. So then we go to part C. It says calculate the moles of water loss. Well, I know that my compound lost 0.90 grams of water because that's how much water was removed when I heated it. And so I'm going to start with this as my given, and I'm just going to convert that mass to moles. So 0.900 grams of water. And again, if I don't want to type water again, I just simply copy that. And then I find the molar mass of water. We found this in our notes. It's actually 18.02 grams of water is equal to 1 mole of water. And so this is equal to, and we put this in our handy dandy calculator, 0.04994. And quite frankly, this should be 3 sig figs. So we're going to just put 0.0499 moles of water. Again, if I don't want to type water, I already have it saved as a copy and paste. But I go ahead and copy this answer, add math, that saves it, and then lastly, paste it into the response box so that I get credit, because you need to answer in both. You need to show your work and the response box filled in order to receive full credit. All right, and so lastly, we're on D. In part D, it says determine the formula unit of the hydrate. So the way I figure the formula unit of the hydrate is I got to find the mole ratio between the anhydrous copper sulfate and the hydrate. And so I do this by taking the moles of the water divided by the moles of the copper sulfate. This will give me a whole number ratio. And so I'm going to do that. And so what we'll take is D, and we're going to find our multiplier. All right, this is going to be the moles of, this will basically be the moles of water. All right, this is going to show us the ratio. And so we get this by obtaining moles of water, and it's actually mole ratio. It's just a mole ratio. It's not saying mole ratio of, this is water to copper sulfate, CuSO4. That's what it actually is. So moles of water to copper sulfate, and then this is moles of CuSO4. Okay, and then now all we have to do is plug these values in, and we get moles of water is 0.0499. And then we have the moles of copper sulfate. And it's not really important to have units here because they're going to cancel anyway. 0.01001. And we end up with something like 4.994, and which is approximately, if we were to round this, it's approximately 5.00. All right, and so we know the ratio is 5:1 water to copper sulfate. So we know that for every 1 mole of copper sulfate, we have 5 moles of water. Well, how does this affect our formula? Well, we simply write copper to sulfate, write the formula, and then we can hit the arrow over to come up. We hit the star button for a dot, And then we're going to say, so that's 1 mole of copper 2 sulfate dot times, and we're going to say 5 and then H2O. And that's just saying that we have 5 moles of H2O. And whoops, we got to make sure we hit the arrow over and then we get it to O. And there we go. And we'll copy that and save. That's the answer. So where do we get the 5 from? That 5 right there is driving this answer here, because there are 5 moles of water for every 1 mole of copper 2 sulfate. And so that's how we're deriving our answer, and that's what we get there. And so that answers question number 1. Let's move on to question number 2. All right, we move on to question number 2. And here we have a chemist. And again, we're using the same ideas that are expressed up in this written portion and also in your study book that I provided you with. But in example 2, it says, imagine a chemist has an unknown solution containing chloride ions. They want to determine the mass of the chloride ions present in a specific volume of this solution. They can do this by reacting the chloride ions with silver nitrate, which precipitates silver chloride, which is a solid. Okay, so if you remember from our solubility rules, when we have silver chloride, chlorides are mostly soluble, except for when paired with silver, mercury, or lead. And so since this is paired with silver, it's going to form a solid. And when we get the mass of that solid, we can determine from that how much of that is chloride ion. Now, the key here is to make sure that we, when we react this, when we do this reaction, we're reacting the chloride ions with silver nitrate solution, but the silver nitrate solution must be in excess. So meaning it is the excess reagent, and that the chloride solution is going to be the limiting reactant, because we want to make sure that we get all of the chloride into the solid. And if we leave any out, then we're not going to really know how much of that chloride was in that solution. All right, so the steps are to measure the volume of the unknown solution. We say that it's 50 milliliters. We react the silver nitrate with excess silver nitrate of known concentration. It's some concentration. We're saying that's an example. It's not important here. All we need to know is that it is excess. This ensures that all of the chloride ions in the unknown solution react to form the silver chloride precipitate. So according to this reaction, and this would be the net ionic reaction, we see the silver ion from the silver nitrate is reacting, and there's going to be a whole lot more of this than there are chloride ions. So we'll have silver left over. But all of the chloride ions will react in forming the silver chloride. So all of the chlorides in the solution, chloride ions in the solution, are captured in the solid. So now this is extra, but a test can be done to make sure that indeed you did use an excess amount of silver nitrate, because it would be hard to know if this is an unknown solution. That's not important for this scenario. Just wanted to put that out there. You can do a test to make sure that it was indeed excess. So then the last part is you're going to separate and dry your precipitate. We've done this in a filter. You dry that, you take that, and you get your yield off of that. Then thoroughly wash your precipitate with distilled water, remove any remaining ions, and dry completely to obtain a constant mass. So we weigh the silver chloride precipitate. After drying, the student weighs the pure dry silver chloride precipitate, and the mass of the silver chloride obtained is 0.7167. So we've taken that precipitate, we dried it. So there's no water on the precipitate, and now we know this is dry silver chloride, and we can determine from that how much of that is chloride. So it says, first of all, calculate the moles of silver chloride. So we have to figure out the moles of silver chloride. Okay, so we have the mass of silver chloride, and so we're going to determine the moles of silver chloride. So our mass of silver chloride is 0.7167 grams. And we can see that on our chart. Make sure you can see that, 0.7167 grams of silver chloride. So this is part A. So we'll label it part A. And we'll say 0.7167 grams of AgCl. It's always important that we label our substances, because when we get to balanced chemical equations, we change those substances, and we need to make sure that we're able to track, and most importantly, our graders are able to track what we are doing. I say most importantly, but we want to receive our credit. All right, so we need to figure out here what is the molar mass of silver chloride, because we need to know um, to go from grams to moles of silver chloride. So you can figure that out, but here I'm just going to give that to you. But if you don't know how to obtain this value, you need to go back and look at how to get the molar mass of silver chloride. That is outside of the scope of what I'm going over in this lesson. It's expected that you already know it. All right, and so we go from grams. Notice grams is in the given, grams is in the denominator. They will cancel, and we are converting to moles of silver chloride. So this is equal to moles of AgCl. Plug this into your calculator, 0.7167 divided by 143.32, and you end up with 0.005001 moles of silver chloride. And so that takes us through part A, is it asked us how many moles of silver chloride are, or to calculate the moles of silver chloride. And so we did. We already were given the mass, and now we converted to moles. Now it says use dimensional analysis to find the moles of chloride ions. All right, so now all we have to do is figure out the moles of chloride ion from this situation. And we're going to have to use dimensional analysis to do that. And this is actually pretty easy, because in silver chloride, in 1 mole of silver chloride, there is 1 mole of chlorine. And so we see that there is no subscripts. So that means there's 1 mole of silver chloride equals 1 mole of chloride ion. So our answer really is going to be easy to calculate it, because we're going to just multiply by 1. So we have 0.005001, and this is moles of silver chloride. And then we're just going to use the established ratio found in the formula unit of silver chloride and say 1 mole of AgCl is equal to 1 mole, and it's not just chlorine, it's not the atom, it's chloride ion, right? It's the chloride ion. So when this breaks apart, it breaks apart into Ag1 plus and Cl1 minus. And so now it lost an electron in obtaining that negative charge, but electrons have such a small mass that they're not factored in to the overall mass. But we're not trying to find mass here, we're finding moles of chloride ions. And so all we have to then do is say this is 0.005001 moles of chloride. And that's all there is to that. And so we have part B done. If we want to, we could even put our answers in a rectangle, and we know that's what they are. And very important that we take our answer, we place it in the answer box. So I forgot to model that, but we haven't left the question yet, so it's not too late. So we plug that in, and then we do the same thing over here. Notice that the numerical value is the same, but the answer is not. One says silver chloride, one says chloride ion. And so they're in that sense, radically different answers. All right, we go to part C. And in part C, we see calculate the mass of the chloride ions. So we know we have 0.005001, whoops, I went too far, 5001 moles of chloride ions. I probably already had that in my calculator or in my saved. And then we're going to multiply this. We're going to say 1 mole of chloride ion is equal to 35.45 grams of chloride ion. And again, yes, it's missing an electron, but I went to my periodic table and I look and see that chlorine is 35.45 grams per mole. So I plug this into my calculator, and what I get is 0.17727. That's a little too many sig figs. So 1.772 grams of chloride. There we go. Because it should be, that's 4 sig figs, and that's what 4 sig figs. All right, and that looks right to me, unless 1.17727. So this should maybe be a 3. All right, so that's what we get there, and we can copy that as a unit and the substance in the answer. So we are feeling good about that. And then paste, and we are done with that. Part C is done. Again, Maybe I put an equal sign where I don't need to do that. There we go. And that will key wrong because of it. So I get that out of there. All right, there we go. And then we can place a rectangle around that as well. All right, if you want to show a lot of separation, not required, but you can show there's a line here between that one and that one. It looks all good. All right, so we're all done with question number 2. Now we go to example number 3 and example number 3, and then this will be the end of this video, and I will start another one on a different section. But these are 3 like lab-based questions, so I wanted to go over these together, and then I will go over another set in a separate video. All right, on this, what we're looking at is a reaction. An experiment is performed to measure the mass percent of calcium carbonate in eggshells. 5 different samples of the calcium carbonate of known mass react with an excess 2 molar hydrochloric acid in an identical sealed reaction vessels. The pressure of the gas produced is measured with a pressure gauge attached to the reaction vessel. Since the reaction is exothermic, we should know that exothermic means it's giving off heat. The reaction system is cooled to its original temperature before the pressure is recorded. So the experimental data are used to create the calibration line below. All right, and so this is creating a calibration line, and we can show you how to use that and determine what we have. So on part A, it says, what is the pressure of gas produced by the eggshell sample? All right, so the eggshell sample shows that we have a 0.200 gram. Prior to the reaction, we were at 0.8 atm. And after the reaction, after it took place and it was cooled, it was 0.870. And so we can't just say that the vessel went up by 0.870 because it had an initial pressure of 0.8 even before the reaction took place. So what we're going to look at is the pressure at completion and the pressure prior to completion in order to determine the pressure produced by the reaction of that shell with hydrochloric acid. Okay, so we're going to place that in there. And we see that right there. We got that. And so this shows us the pressure produced is equal to pressure after completion, or at completion, pressure prior to completion, after and before, right? At completion or after, and prior to or before. And so we just plug in some values there. And so let's do that. And we end up with, and I'm making this look a little bit fast on this just because I don't want to take too much time on your video here. But that's what that should look like. And we are done with that. And so the pressure of the of gas that was produced by the eggshell sample is 0.070, and then unit is atm, or atmospheres. So now, why is that important? Because according to the calibration curve, so they made this calibration curve, and we look at it, and we can see that there's a correlation between mass and pressure. All right, and so we determine the pressure. This is our dependent variable. I'm going to find our independent variable. So from the pressure, we can say, okay, well, we had a difference of pressure of 0.07. So we start there, we go to the line, and then we go to the x-axis, and we see what that mass is associated with that pressure change. And so what that looks like is this right here. Again, I probably need to label my section here. Let me go ahead and label this as A. Model this properly. All right. And then lastly, we need to go to B. All right. And here I'm going to kind of show a picture of what this looks like. So just so that we can see where I'm getting these values. Whoops. Yeah, that's going to work. All right. And let's go escape and Control V. All right. So here is my picture. And this whole thing shifted. If you don't like that, you just move it over with a little hand. And so we can see on this picture We started at 0.07, and that is associated with some value between 0.14 and 0.15. And so I'm going to estimate where it is between 0.14 and 0.15. And my estimation is going to be this right here. So let me put that in there. Where are you guessing it's at? So you can guess wherever, as long as it's in between those values. I see it at this value right here. And so according to the calibration curve, what is the mass? I'm seeing it at 0.0143 grams of calcium carbonate. While I may not have every value keyed, we should be able to see 0.14, and then we'll make an estimation between 0.14 and 1.5. And so I'm guessing that it's 0.143. You may say it's 0.144, 0.145, 0.142. All of those would be correct, whether they're keyed or not. I'll go back and key them later on if need be. And then lastly, it says calculate the mass percent of the calcium carbonate in the eggshell. And so we can do that real easily by taking the following values. All right, so we're going to take mass percent of the eggshell, of the calcium carbonate in the eggshell. Let's say that. Oh, hopefully I copied this. Let's say Control C. All right, save. All right. And so what we end up with then is this here, and this is B. We come up with this formula, and this formula tells us the mass percent of calcium carbonate is the mass of the calcium carbonate divided by the total mass. And this shouldn't be new stuff to you, because you've done mass percent calculations before, and basically you're figuring out the mass of the part divided by mass of the total times 100. And so that's what's here. We're interested in the mass of just the calcium carbonate divided by the total mass of the eggshell. And so we have both of those values now. And so we just plug those in. The mass of the calcium carbonate that we got from the calibration curve was 0.143 grams. And the mass of the eggshell is 0.200 grams. We get that right from the chart. Again, these units are going to cancel, so there's no need in placing any other values in there. And then we're going to multiply that by 100%, and we end up with 71.5%. So the eggshell is 71.5% calcium carbonate. So there you have it. If this was true data, well, then we have our eggshells have a lot of calcium carbonate. So 71.5%. All right, and so that's where I'm going to end this video on questions 1 through 3 of this part. Thank you for watching. Please like and subscribe.